This slide marks the beginning of our review section on pipeline ADCs. We're going to take a closer look at the concepts we've discussed about this important type of analog-to-digital converter. Just as a quick refresher, what's the main idea of a pipeline architecture? Think of it like an assembly line. Instead of one single block trying to convert the entire analog signal to a digital code all at once, the job is broken down into a series of smaller, simpler stages. Each stage performs a partial conversion. It determines a few bits, and then passes the remaining signal, the residue, onto the next stage. Because all these stages can work on different samples simultaneously, pipeline ADCs can achieve very high throughput, meaning they are very fast while still maintaining good resolution. So, in this review, we'll be recapping this fundamental structure, looking at the building blocks within each stage, and likely moving on to discuss the real-world challenges and sources of error that can affect their performance. This diagram shows us the architecture of what's called a generic pipelined ADC. The core idea behind a pipelined ADC is divide and conquer. Instead of trying to convert an analog signal to a high-resolution digital number all at once, which can be slow and complex, we break the problem down into a series of smaller, faster steps. Think of it like an assembly line. Let's follow the input signal, VIN, as it enters the first stage, stage 1. The first thing that happens is that a low-resolution sub-ADC takes a quick look at VIN and makes a rough digital estimate. It resolves just the first few most significant bits of the final digital word, which we call D1. Now, this digital estimate D1 is immediately converted back into an analog voltage using a subDAC. This analog version of our first guess is then subtracted from the original input signal, VIN. What do you think is the result of this subtraction? It's the error, or the difference between the actual input and our first rough guess. We call this leftover signal the residue. This residue contains the finer details of the signal that our first rough conversion missed. But it's likely a very small voltage. So, before passing it to the next stage, we amplify it, in this case by a factor of 2, to the power of n1, where n1 is the number of bits resolved in this stage. This amplification scales the small residue signal back up to the full input range of the next stage, so it can be measured accurately. And that's the pipeline in action. The amplified residue from stage 1 becomes the input for stage 2. Stage 2 does exactly the same process. A sub-ADC resolves the next few bits, D2. A subDAC converts it back. This is subtracted to find a new, even smaller residue, which is then amplified and passed to the next stage. This continues all the way down through stage M. The final residue from stage M is then converted by a final ADC, often a flash ADC because it's very fast to get the last few bits. So now, we have a collection of digital outputs from each stage, D1 from stage 1, D2 from stage 2, and so on, right up to the output of the final flash ADC. The digital combiner, at the bottom, is responsible for putting all these pieces together. It correctly aligns and combines these partial results to construct the final high-resolution digital output, DOUT. The points at the bottom of the slide summarize this. Each stage resolves a small number of bits, N1, N2, etc. The total resolution of the ADC is simply the sum of the bits from all the stages. The output of any given stage, that amplified error signal, is called the residue, and the chain of stages that follows it to digitize that residue is called the back end of that stage. So, the main takeaway is that by breaking the conversion into a pipeline of simple stages, we can achieve high speed and high resolution simultaneously.